Alright, this is also part of section 4.4. It's the average value of a function. It falls into integration. But what the average value of a function is pretty much if you're given a function from a to b and you've got this area under it, the average value is going to be the y value that corresponds to the average of the highest area and the lowest areas. So it's going to be that area that's right in the middle of the whole area from A to B. An easier way to think about this is imagine this little curve as like a wave, and say you dump a bunch of water into a bucket and it creates this wave. The average value is what the height of the water in the bucket would be after the water has settled. So like right when you pour the water in, there's all of these different high points and low points, and there's a bunch of waves and stuff, and you can't really get an exact measurement on what the height is. But the average value theorem provides a way to find out what the value, what the height of the water would be after it settled and it was just one flat surface. So I'm just going to go right into an example. Pretty short video for this one. But find the average value of f of x equals 3x squared minus 2x on the interval 1 to 4. Here you can see our average value formula. It's pretty much just basic integration using which you can use fundamental theorem of calculus, except now you've got this 1 minus ba tacked onto it. So to solve this, 1 over b minus a tacked onto it. So 1 over b, in this case 4, minus a, in this case 1, times the integral from 1 to 4 of 3x squared minus 2x dx. So you've got 1/3 times, if we take the antiderivative of this function right here, you get 3x to the third divided by 3, so that's just x to the third, minus 2x squared divided by 2, so that's just minus x squared, 1 to 4. So 1/3 times of 4 to the third minus 4 squared minus 1 to the third minus 1 squared. So you've got 1/3 times 4 to the third, that's 64 minus 16 minus 0. So you've got 1/3 times 48, that gives you 48 over 3, and that equals 16. So that would be your average value of the function. In the case of my my explanation in the beginning, that would be the height at which the water would settle. Just another quick topic I'm going to show in this one, I guess, is the second fundamental theorem of calculus. We were told that it's unlikely to show up on the AP test, but it is mentioned in our book, and it was on our integral test, so I'll just throw it in this video. what it means pretty much is that if you're given a function and you're asked to take the integral of that function, then once you take the integral of that function, you can take the derivative of that thing that you just solved for, and that equals the original function. So it pretty much says, take the antiderivative, take the derivative, and what you'll end up with is the original function. The main thing you can associate the fundamental theorem of calculus with is when you've got an x as your as part of your boundaries. If the x is the lower bound interval, then you're going to have to apply one of the properties of integration. And just as a side note, that's the property where it says if you have a negative or excuse me, if you have man, we don't even use this enough for me to remember what it is. Anyways, it's in one of the previous videos. I can actually look it up really quick, but I'll just jump right into oh, here it is. The idea that beta a of f of x dx equals negative a to b f of x dx. So that's like, say this x was the lower bound. You could just put a negative sign in front of the whole thing, flip the limits, and you can get your x on the top and use the second fundamental theorem of calculus. Okay, so as for the quick example, say we were given evaluate the derivative with respect to x of the integral from 0 to x of square root of t squared plus 1 dt. First of all, just check to make sure that your conditions apply. You've got the x on the upper bound. You've got with respect to x right there. And so essentially when you do fundamental theorem of calculus, what you're going to do is just replace this variable with the new upper bound variable. I'm sure there's videos on proofs behind this, but as for this one, I'm just going to explain what I would do. I mean, I did that on my Chapter 4 test, got it correct, so I guess it works. But yeah, there's the second fundamental theorem of calculus and the absolute value theorem, or absolute value of a function. Hope those helped